Welcome to this deep dive into one of the most powerful bridges between classical statistics and modern machine learning, principal component analysis, or PCA, specifically applied to solving the problem of multicollinearity. In the world of data science, having more data is usually better, but having redundant data can be a nightmare for our models. In classical statistics, we often use linear regression. However, a silent killer often lurks in our datasets: multicollinearity. This happens when two or more independent variables are highly correlated. Imagine trying to predict a house's price using both its square footage in meters and its square footage in feet. They provide the same information, making the mathematical estimation unstable. Mathematically, multicollinearity explodes the variance of our coefficient estimates. In the ordinary least squares formula, we invert the matrix x transpose x. If variables are perfectly correlated, this matrix is singular and cannot be inverted. If they are highly correlated, the matrix is near singular, making our results extremely sensitive to tiny changes in the data. This is often measured by the Variance Inflation Factor, or VIF. Section 1. The geometric perspective of redundancy. Let's visualize a 2D dataset where x and y are highly correlated. The data points form a narrow, elongated cigar shape. In this scenario, trying to distinguish the individual contribution of x versus y to a target variable is like trying to balance a scale with weights that are glued together. Section 2. Enter principal component analysis. PCA is a dimensionality reduction technique that transforms our original correlated variables into a new set of uncorrelated variables called principal components. It's like rotating our perspective to look at the data from its most informative angle. Section 3. The Covariance Matrix. The heart of PCA lies in the Covariance Matrix. This matrix captures how every variable changes in relation to every other variable. By analyzing this matrix, we can identify the directions, or vectors, along which the data varies the most. Section 4. Eigenvectors and Eigenvalues. We perform an eigendecomposition on the covariance matrix. The eigenvectors represent the directions of the new axes, the principal components, while the eigenvalues represent the amount of variance explained by each component. The first principal component, PC1, always points in the direction of maximum variance. Section 6. Orthogonality and independence. A key property of PCA is that all principal components are orthogonal to each other. In statistical terms, this means they are perfectly uncorrelated. By using these components as our new features, we have mathematically eliminated multicollinearity by construction. Section 7. Practical example, real estate. Imagine features like number of rooms, total area, and property tax. These are naturally correlated. By applying PCA, we can create a size factor, PC1, and perhaps a quality factor, PC2. Instead of 3 redundant variables, we use 2 independent components that capture 99% of the information. Section 7. The trade-off, interpretability versus performance. While PCA solves multicollinearity and reduces noise, we lose the original meaning of our variables. PC1 is a linear combination of all original features, making it harder to explain to a business stakeholder than square footage. However, for machine learning performance and stability, this trade-off is often worth it. In conclusion, PCA is not just a tool for making data smaller, it's a tool for making data better. By transforming correlated features into independent orthogonal components, we build models that are robust, stable, and theoretically sound. Mastering the transition from statistics to ML through PCA is a vital step for any data scientist. References: 1. Gujarati, D.N., Basic Economics. 2. Jolliffe, IT, Principal Component Analysis. 3. James, ETL, An Introduction to Statistical Learning. 4. Hasty, ETL, The Elements of Statistical Learning.